Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about the equivalence principle. We'll describe a simple scenario that has unbelievably profound implications. And here's the scenario. We've got a elevator and a character, passenger in the elevator. We'll call the passenger Al, and Al is standing on a bathroom scale. And what we want to imagine is what happens if the elevator accelerates. So the elevator is undergoing some acceleration, and for specificness, we'll assume that it's accelerating in the upward direction, constant acceleration. And we'll also assume that Al has a mass, which we'll call mAl. And the question is that we want to ponder is what will the bathroom scale read under these circumstances? And just as importantly, or perhaps more importantly, how will Al feel? What will the sensation be like for Al to be riding in an accelerating elevator? And if you think about it, you've all experienced this. When you start off at an elevator, the elevator is at rest, presumably, and then it starts up, and there's a brief moment before as it gets to its sort of cruising velocity in which you're accelerating. So I want you to think about how you feel during that acceleration phase in the elevator. So let's dig in. So, as has become our habit, let's analyze this situation using the framework of Newton's laws of motion. And of course, we're going to start off by drawing a free body diagram. And I want to draw a free body diagram for Al. The body in this free body diagram is going to be Al. And so Al will, of course, experience a downward going gravitational force. That's the gravitational force on Al, and that is equal to Al's mass times g. And in addition to the gravitational force, which acts at a distance, we want to examine the situation for contact forces. What is touching Al? And of course, the only thing touching Al in this scenario is the bathroom scale. So there's going to be a contact force that the bathroom scale exerts on Al, and it's going to point in the upward direction. So we'll call that the force of the scale on Al. Okay, next we will apply a Newton's second law to the situation. So Newton's second law says that the net force that acts on Al is equal to Al's mass times his acceleration. And the net force, if we look at our free body diagram, there are two forces that appear in the free body diagram acting on Al, the force of the scale on Al and the force of gravity on Al. And now I just want to rearrange this equation. I want to solve for the force of the scale on Al. And just by rearranging, the force on the scale of the scale on Al is equal to the mass of Al times the acceleration of Al minus the force of gravity on Al. And the acceleration of Al, of course, is the same as the acceleration of the elevator. And the force of gravity on Al, we can just write as Al's mass times g. And I can just combine the terms and say that the force of the scale on Al is equal to Al's mass times the acceleration of the elevator minus g. So A elevator minus g, this little drawing that I've made here sort of shows you what that means. G, of course, points downward. We've assumed the elevator is accelerating upwards. When you calculate A elevator minus G, you get an upward going arrow. And the bigger A elevator is in magnitude, the longer that arrow is going to be. And that tells you that if the elevator is accelerating upwards, the force that Al experiences on his feet will be greater. So as far as Al feels, he's going to feel heavier, if you think about it. He's going to feel like he weighs more than he does when the elevator is standing still. And if you ride in an elevator, you're say on the ground floor of the Science Center and you press penthouse, you will feel during that acceleration phase like you just got a little bit heavier. And now we wanted to know, what will the scale read? Well, the scale reading depends on the force that Al exerts on the scale. So let's use Newton's third law to write that down. The third law says that the force that Al exerts on the scale, that's going to determine what the scale reads. That, by virtue of the third law, is equal to minus the force that the scale exerts on Al. And that is just equal to, if we put a minus sign in front here, it's going to flip the order of these around. So we can write this as M Al times G minus A elevator. So the reading on the scale, the important conclusion is that it depends on Al's mass and on the difference between this G, the acceleration due to gravity, and the acceleration of the elevator. And you really can't tell from the reading, and this is the important point, exactly how much of the contribution is due to G and how much is due to the fact that the elevator is accelerating. All you know is something about the difference between G and the acceleration of the elevator. And what the scale reads, another name for the reading on the scale, is your apparent weight. And what the scale reads is the magnitude of this force, the magnitude of the force that Al is exerting on the scale. So we're going to call the apparent weight W sub apparent, and your apparent weight is equal to the mass of the person standing on the scale times the magnitude of G minus A elevator. So this result, we can generalize it to explain what happens when you are in a reference frame that is accelerating at the value of G. So if you are in some sort of elevator or perhaps rocket capsule, and the capsule is accelerating at G. So if the capsule is subject to the force of gravity, its acceleration will be G. And in that case, the acceleration of your reference frame, if it's equal to G, then your apparent weight in such an environment will be zero. And this picture, which I've taken from the Wolfson text, sort of captures exactly why you feel weightless when you're in orbit around the Earth. Everything is accelerating downward with the same acceleration, which is equal to G. So you can say the capsule is falling, you're falling, the book is falling, everything is accelerating downward with the same acceleration, which is all due to gravity. So the acceleration of everything is G, and therefore, relative to the capsule, you're not going to accelerate at all. So that is why you feel weightless in orbit around the Earth. Or more generally, when you are in any reference frame that is subject just to the force of gravity, you will feel weightless. So you don't have to be orbiting the Earth. You could be cruising to Mars. The way you get to Mars is you get in a rocket, and the rocket fires its engines, and while the engines are firing, the acceleration of the rocket is not subject to just to the force of gravity. There's thrust from the rocket engine, but once the rocket engine shuts off, the only force that acts on the rocket and everything in it is the force of gravity. And in such an environment, you are going to feel weightless. And that's an issue if you're trying to get to Mars. It's a long trip, 7 months or so to get to Mars, and you will be weightless. You will feel weightless the entire time. Now, it doesn't mean that there is no gravitational force acting on you. There is. That's the whole point. But relative to the rocket, the sensation will be one of weightlessness. So when Al rides in an accelerating elevator, that's an example of what we can refer to as a non-inertial reference frame. And what exactly do we mean by non-inertial? Well, it means an accelerated frame of reference. You're making measurements in a environment which is accelerating. So we're going to refer to that as a non-inertial reference frame. And it's at this point we can really begin to understand the content of Newton's first law of motion. So you may remember in the What's the Big Idea on the First Law, I said we would come back to explain exactly what the point of the first law was. So the way the first law is generally stated is something like if the net force on an object is zero, then its acceleration will be zero. But an important caveat is Newton's first law specifies that we have to be talking about measurements made with respect to an inertial reference frame. Well, what do we mean by an inertial reference frame? Well, you can think of Newton's first law as the definition of an inertial reference frame. If you go into a frame and if you observe that when there is no net force on the object, its acceleration is zero, then you know that you are in an inertial reference frame. So let's imagine a situation in which Al and his elevator are nowhere near any gravitational source. They're in deep space. There's no gravity where they are where he's standing, and the elevator is accelerating. So Al will experience a net force. There is still the force of the scale on his feet. The scale will read the magnitude of that force, and yet Al will notice that relative to the elevator, he is not accelerating. So therefore, Al will conclude that he is not in an inertial reference frame, and Newton's first law is not valid. So you can think of Newton's first law as sort of a test to see whether or not you are in an inertial reference frame. If you go into a frame where you experience a net force and yet your acceleration relative to that frame is zero, that is conclusive evidence that you are not in an inertial reference frame. So there is sort of an intellectual content to Newton's first law. Basically, you can think of it as a way of defining what we mean by an inertial reference frame, or at least testing to see whether or not you are in an inertial frame. So now we are in a position to discuss this very important principle, the equivalence principle. So I want you to consider two different scenarios. One scenario, scenario one, is that Al and his elevator are somewhere far from where there's any gravity. So G in this place is equal to zero. And the elevator maybe has a little rocket engine strapped to it. So even though you're in deep outer space, you can fire the engine and make the elevator accelerate upward. And this is one situation. And let's imagine that the value of the acceleration uh, of this acceleration, the magnitude of it is 9.8 meters per second squared in this sort of upward direction. So that's scenario one. Scenario number two is that the elevator is at rest on Earth and therefore has zero acceleration. But of course, there is gravity on Earth, and the value of g in this environment is a minus 9.8 meters per second squared. And what the equivalence principle says is that you really can't distinguish these two situations. If you were in a if the elevator was sealed and Al had no way of looking out the window, he could not tell whether the reading on the scale that was being measured was due to the fact that the elevator was accelerating or whether there was gravity. And that is what is meant by the equivalence principle. It means you can't distinguish from being in an accelerated reference frame and another situation in which the reference frame is not accelerating, but in which there is a gravitational acceleration. And of course, Al is none other than Albert Einstein. And it was Albert Einstein who, in formulating his theory of general relativity, really elevated. People had understood this situation long before Einstein came along, but Einstein elevated it to a fundamental principle of nature that, in principle, you could not distinguish between being in an accelerated reference frame and the effects of gravity. And that ends up having profound effects because, for example, it means if you were to shoot a light beam through through an elevator that was accelerating, relative to the elevator, you would see the light bend. And if you really take the equivalence principle seriously, it means that if a light beam travels where there's gravity, the light beam is going to bend as well. So that was a consequence. The equivalence principle is really the starting point for Einstein's theory of general relativity. And one of the predictions of the theory of general relativity is that when light travels in a strong gravitational field, it will bend. And that was a revolutionary concept at the time, and it led to an exciting situation. You know, Einstein developed his theory of general relativity it was published in 1916 or so. So the theory of general relativity is a theory, and that's in 1916. And it made a prediction that when light travels in a strong gravitational field, it should bend. But it was just a theory. What you want is an experimental test. And people quickly realized that during an eclipse, the light from the stars come out during an eclipse, and there would be a situation in which light from the stars would pass very close to the sun, and the sun's strong gravitational field would bend the light. And so it was very exciting. In about 1919, there was a solar eclipse, and people went out and they measured the position of the stars, and lo and behold, they saw the effect of the light bending as it passed near the sun. And it led to this rather fantastic headline. It was front page news in the New York Times, the august New York Times, and they sort of really knew how to write headline titles back in the day. This is one of my favorites. Lights all askew in the heavens, more men of science, more or less agog over results of eclipse observations. Einstein theory triumphs. Stars were not where they seemed or were calculated to be, but nobody need worry. So no need to worry, even though the lights are all askew in the heavens. And that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.